Now you can start. So you need to explain your idea first, and then you start coding. After after coding, you need to tell me the time capacity and the space capacity, and can you start your timer when you start the code this question? Yeah, yeah, you can start now.
So today we're going to solve weak code number 76 called minimum window substring. This is a problem that's asked by Airbnb a while ago. And as the title says, it's trying to find the minimum window substring. So we're given two input strings, one called S and one called T. S has a length of M, T has a length of N. And we want to return basically the smallest part of S that has everything in T, including duplicates. So if T has AABC, then S must have at least AABC, for example.
Mm-hmm.
And then the minimum window substring would be this part right here.
Yeah.
And if there's no such substring, aka if S is less than T, then we're going to return an empty substring, or none of the characters inside of S show up in T. So S is going to be, well, we can choose either string to slide our window through, but we're just going to use S because we want to use S to satisfy T. So you can think of S as kind of the test taker, if you will. It's the bigger string here, but it doesn't have to be. Here you can see S is smaller than T. So first of all, let's take care of some base cases, because obviously if S is less than T, then we can't return anything. So what we're going to do is we're going to slide our window through S. So let's take an example. A, D, O, B, E, so C, O, D, E, B, A, N, C. So we're going to slide our window, and we're going to add it to a dictionary called need. Need from T, because this dictionary will represent the letter we need from T and how many we need from T of that letter up to the current point. So, for example,
So
we need
the,
one A, we need one B, and we need one C. So in the beginning, the dictionary is going to be just like this, telling us how much we need from S to satisfy T.
oh, I have one question. So what is the data structure you use for the dictionary?
This is just a key value pair store. It's called a
So
hash map, a
oh,
dictionary, whatever you want to call it.
okay.
All the keys have to be unique, right? And they can map, the values don't have to be unique, but the keys have to be unique. And so, yeah, and then when we build our dictionary, which is pretty easy, we're going to loop through S, and we're going to basically say we see an A in from S, so we're going to decrement this. So we're going to make this 0 now, because we don't even need any more A's from T. And then we're going to keep sliding our window. When we get here, our dictionary is going to look like this. Then by the time we get here, we're going to have satisfied T all the way. So this meaning is the same as basically we need nothing from S. Okay, cool. So we have a substring of S right now that is satisfied T, but we also want to find a minimum window substring that satisfies T, which is actually BANC. So what we're going to do as soon as we fully satisfy S is we're going to shrink the window. So we shrink the window from the left, and this becomes DOBEC. And cool. So now we have to reflect the current state of our window in our dictionary at all times. So because we removed a character that contributed towards our progress, now we have to add it back. So our dictionary now has to,
A increased by
now has to
one, right?
become 1, because we need exactly one more A, because we moved it out of the window. So the dictionary will always keep track of the state of our current window.
Okay.
And cool. So now we're not even satisfying T completely. So we're not satisfying t completely. We need to expand the window.
Okay.
Now we get to O.
So you have 2 pointer,
Doesn't
right?
make the progress. What's that? I mean, I'm just explaining the concept right now.
Yeah.
Uh,
I think you are using a 2 pointer, right?
no, I'm not.
Okay.
I'm using sliding window technique.
Yeah, it slide the window, right? Because you had 2 pointer. 1 pointer go right.
Yeah, but it's called a sliding window. 2 pointers is a
Yeah.
different technique.
Okay. Okay.
So, okay. So we're still not satisfying our window, so we have to keep increasing until we're satisfying. So you can see this is still not satisfying because we don't have that A. Okay, now we're satisfying T.
Okay.
So, except that this is not the shortest one. So we're going to have to reflect all these changes in our dictionary. So at this point, we fully satisfied T. So our dictionary looks like this, but this is not the smallest one. So what are we going to do? We're going to shrink the window from the start.
Mm-hmm.
So we're going to go here, but the window the letter we kicked out of our window is not contributing to our progress. So we don't care about that. We're going to keep shrinking. Again, same thing. O is not part of T. So now we actually need one more B. So B actually becomes -1. Well, sorry. We need one more B, so B becomes 1 now. And then we're going to, well, we're still not satisfying our window fully. So now we have to slide forward again. So right now we're at this portion. So we're going to go to N. Still not satisfying T completely. Now we are satisfying T completely. So when we're satisfying T completely, again, this is going to be equal to 0.
Yeah.
And then, but this is not the smallest result we can find. So we're going to shrink the window again. C, again, E doesn't care. C does care. So now we need one more count. One more C from S. And so we're going to keep shrinking again. Again, oops, did I make a mistake? Nope. We don't care about O. We don't. Okay, next we don't care about D. We don't care about E until we get to this point,
Yeah.
which if we shrink the window, we don't have a fully satisfied T yet. So if we go A and C,
Okay.
then we
A.
need one more B and one more C to satisfy T. So this is not a valid window. So then this is going to be our minimum window substring.
Mm-hmm.
And yeah, when by the time, in this case, the end pointer of our window reaches the end of S, we will have a result, which is going to be B, A, and C, because in each iteration, we're going to save the dimensions of the window in a variable.
Mm-hmm.
And then we're going to, at the end, the smallest window is going to be B, A, and C because we're shrinking the window as long as we're satisfying T completely.
Mm-hmm.
So yeah, let's code it up now.
Okay. Let's start it. Sound good? No, your
Let's
solution is
take care of
good.
our base cases. So if length of S is less than length of T, then we're going to return an empty string according to the instructions. Because it's not possible to satisfy T if S is already of a smaller frequency than T.
Mm-hmm.
If that's not the case, then we can satisfy T with S. So we're going to declare a window end pointer as the beginning of a window. We're going to declare a variable called start saver and end saver. End saver is always going to be float infinity because the window is going to be always less than infinity.
Mm-hmm.
And then to declare a variable called matched, which is going to count the number of keys in our dictionary. And if the number of keys in our dictionary match T, then obviously we satisfy T. So this is going to be the determining factor of whether we found a possible solution, not necessarily the shortest.
Okay.
So now we're going to choose S to slide our window through. So window N gives you the index, char gives you the value. And before we do that, we actually need a dictionary to keep track of the current state of our window and how much progress we made. So if char is inside of need from S, meaning it exists, if the current character we're seeing exists as a key in our dictionary, then we made at least 1 unit of progress, or we made exactly 1 unit of progress. So for example, if we're going from, let's say, we have 0, 0, 1, and then we're satisfying the last one, 0, 0, 0, then we're matched. So if need from S char is equal to 0, then matched plus equal to 1, because we satisfied one of the characters inside of T. And then if we satisfied one of the characters of T, again, match is going to be the determining factor. So if matched is equal to the number of keys in the dictionary, then we satisfied all letters of T. And the reason we use a while loop here is as long as we're satisfying, we have to keep shrinking the window because we want the smallest window. So that's why we cannot use if here, because that would only check the conditional once, versus we need to keep checking the conditional forever as long as this is true. So cool, we have a possible solution. Now we need to save the dimensions of the window. So if n saver is bigger than window n minus window start plus 1, and the question is asking in terms of length. So because these are indices, and indices are always 1 less than length, we use the plus 1. And n saver is float of infinity, so it will always be bigger than the window. So n saver will be the length of the window, which is window start minus window n minus window start plus 1 at this point, and the start saver is going to be at the beginning of the window.
Okay. Very nice. Now,
So we found this is always going to be true in the first condition, in the first iteration. So now we found a result. We're saving the dimensions of the pointer in case we need them in the future. Now we can shrink our window. So let's call this the character to kick out, which is going to be the letter that we're going to, move away from, kick out from the left side of the window.
okay.
And this is going to be the actual shrinking of the window, because we're using window start to keep track of the length of the window. And the reason we use kick out here is because we want to see if the letter we kicked out was used as progress. So if kick out in need from S, then we have to roll back the progress once, especially if need from S kick out was equal to 0, because equal to 0 means that the balance was perfect. That means we satisfied it. If it's -1, then we have too much. If we have 1, then we need 1 more. So we have 1 too little. So this means that the balance is perfect. If that's the case, then we got rid of that perfect balance. So now we need 1 more. And first of all, because matched is the determining factor of the entire S, we need to do that. And then we also need to say we need 1 more. So we matched, the bigger matched is the closer we are to a result. The smaller the value in the dictionary is, the closer we are to finding an answer. And so at this point, we've slid our window throughout S. So we know we have some kind of an answer, and these 2 pointers will do their job here as saving all the possible results, which will end up with BANC, for example. So at the end, obviously, we're asked to find the smallest part of S. So if length of S is bigger than the n saver, which is the dimension of the last possible smallest window, then we know that we have a valid result. So we can return a portion of S based on the boundaries, because start saver is going to be the beginning of the window and end saver is going to be the end of the window. So including the index of start saver and then start saver plus end saver is going to be the actual length of the window. if length of S is equal to n saver, then we can just return S because that's going to be the same string. The string is just going to be of the same length, and we know we already satisfied T when we got to this point.
Mm.
And then in any other condition, then we don't have a valid answer, so we can just return an empty string.
Okay.
And I wanted to also point out that here, after we do this, we always have to ask this question because we're still satisfying T. For example, let's just say right here, we're satisfying T, we're still satisfying T. So we have to ask, while matched is equal to length of nums, because matched will still be equal to the number of keys in the dictionary. Because we only incremented matched when we found the number of the keys in the dictionary restore their perfect balance. Because the smaller this value becomes, the closer we are to finding an answer, the larger this answer becomes, the closer we are to finding an answer. So hopefully that makes sense.
Yeah,
but
makes
let's run
sense.
it.
Yeah. Oh, wow.
So as you
Okay.
can see, it passes all the test cases, hopefully.
Okay.
And
Yeah.
so the time complexity of this solution is O of log n, because we're using a sliding window technique to basically
Why is
make
log
the optimal
n?
decision.
I have a question. Why is
Because
log
log
n?
of n is better than linear time complexity. This is not a linear time solution because sliding window is of log n time complexity.
Oh, but this one is b of n, right? I saw the time complexity is b of
Did I
n.
say that?
Mm-hmm.
Let's see. Or does it say that?
Yeah, it's b of n, I think. Oh, he can help us analyze the time complexity.
Looks like, well, sliding window is generally O of log of n, and we're doing that because, again, we're only sliding the window through one of the strings, so we're already saving time complexity there, and we only have to slide the window through the one of the strings once.
Yeah, so it should be.
And that's a neat trick about it. Because depending on the length of S, if S is really long, then we're still on the order of, so it's supposed to be O of log n, I guess, because n is the length of S, which is one of the strings. S, we don't know if S is going to be smaller or bigger than T, but we're just using it because we know S has to satisfy T.
Okay.